Now, this is the original circuit that were in the lab book, right? Is this it? So we have a 100 ohm resistor for RC. We have a 33K ohm resistor for RB. And we have two variable power supplies, so we can adjust the collector voltage and we can adjust the base voltage. The emitters connected to common. Now the problem we have with using the variable power supplies on the trainer. So the variable power supplies on the trainer are right here. These are fixed power supplies over here. These are our two variable power supplies. We have a plus variable power supply and we have a minus variable power supply. And the controls for the power supply are right here. These are the two controls for the variable power supplies that's built into the trainer. Now, what's the problem? What type of power supplies do I need? What's this power supply? Is it a positive or negative supply? We look and see what's referenced to common, and the power supply is whatever's not referenced to common, right? Huh? So this is a positive. The common is the common of the circuit. So if I was to come over here and take a black meter lead and I was to hook it right there, is it going to measure positive? Is it going to measure negative? If I hook my common, and here's the positive of the power supply, the negative is connected to common. So what's it going to measure? Is it going to measure positive? Is it going to measure negative? Okay, so this is a positive power supply. Okay, is this a positive power supply or is this a negative power supply? Okay, positive. When I look at the two power supplies on my trainer, what do I have? I have a positive and a negative. Y'all understand that? So I can use this power supply, but I can't use that one. Y'all understand why? Yes or no? Well, the power supplies on the trainer are laid out like this. So what we got is we got one variable power supply pointing like this. We got another power supply pointing like this. This goes to the little terminal on your board. This side right here goes to the little terminal on the board. And these two guys right here are connected together, and this goes to the black one that's labeled ground. So this one uses a negative ground. This one uses a positive ground. What do I need? What's this one? No, what's this ground? What's this ground? Negative. This uses a positive ground. This uses a negative ground, which means I can't use the negative power supply. So what do I do? How do I hook this circuit up? Well, guys, I've got 8 power supplies on that bench in there, right? You understand? So all I got to do is just go in there and get one of these big brown power supplies and have it set right here. Okay, y'all understand? It's got a positive supply. It's got a negative supply. The only thing I've got to do, so I'm not using the power supplies on the trainer. I'm sorry, I'm using one of them. I'm using that one over there. Okay. So I come over and I've got this other power supply over here. What do I need to do? Well, I got to establish the same common, so I have to run a jumper right there. Now the two power supplies have the same common, right? You understand? And then I can use this power supply over there. Y'all understand that? So you guys, this is the little kind of stuff you got to figure out. Another problem I have is that power supplies never go down to these variable power supplies can't get down to 0. So the first voltage I need over here, what's the first current? What's the first base current I need? So I'm looking at IB. I'm looking at the chart for the question. I'm looking at 50 microamps, right? Okay, 50 microamps. What voltage would this resistor right here have to drop to get 50 microamps if 50 microamps flow through it? What's V equal to? What's Ohm's law say V is equal to? Okay, so I need 50 microamps. And what's the size of the resistor? Okay, 33K. What voltage drop would I need across that resistor to get 50 microamps to flow? One point what? 1 point, yeah. Okay. Well, I cannot adjust the power supply on the trainer down to 1.65 volts. So what do I need to do? I'm not going to change the resistor. I'm doing something else. We could lower the resistor because we need to get to set up this chart. We need to get 50 microamps, or we have to redo the whole chart, right? So one of the suggestions that Mitchell made is change the size of the resistor. We wanted to drop less voltage at the same current. So what I use a higher size resistor or a lower size resistor? I wanted to drop less voltage at the same current. Well, if V is equal to I times R, and I'm not going to change this, times some R, and I want it to be less, I'm not going to change this. If I'm going to make this go down, R's got to do what? If I'm, Okay, so let's do that. Let's say V is equal, and some of y'all are answering right, but most of y'all are answering wrong. Let's say 50 microamps, and I want it to do 50 microamps, right? You understand? Okay. I want to get the same current, but I want it to do what? Or maybe I'm wrong. So we want it to do the same current and drop more voltage, right? Because I can't adjust this down to what? The minimum I can do on this is around 2 volts. And what do we need? We need 1.65 across that resistor. So our power supply would have to go through, I don't know, we might be able to do that. I'm going to add 0.7 of a volt to this. What would the power supply have to go to? 0.35. I might have could have done that, guys. I might have did something for nothing, but I'm not going to rewire it. But if we wanted to change the resistor, what would we want it to do? We'd want it to drop more voltage at the same current. So I told y'all wrong. If I was wrong, I apologize. It's been recorded. So what would R need to do? Yeah, R would need to go up. Sorry, guys. So we'd have to drop more voltage at the same thing. But that's not what I did. So what did I do? I used a what? A pot. Not a rheostat. Why not a rheostat? Well, no, a rheostat doesn't control the voltage. A rheostat controls the current. Okay, y'all understand that? But I'm not through yet. Hold on. You're right, but I don't have the pot up there. No, that's not the symbol for a rheostat. This is not a symbol for a rheostat. This is a symbol for a variable voltage source. Okay, so that's a power supply. That's a symbol for a power supply. So this is the symbol of a DC power supply. Could be a battery, but that's a symbol we use for all DC sources now. And anytime I come over here and put an arrow through something, it means it's what? It means it's variable. This is the symbol for a rheostat. So it's drawn like a resistor, and then we put an arrow through it. Okay, that's a symbol for a rheostat. A symbol for a pot is not a rheostat. A symbol for a pot is the same symbol, but then we put an arrow coming in the side. Now, a pot is a variable voltage divider. So that means we can adjust that. We can, if I've got 10 volts up here and common on there, then I can adjust this wiper to get anywhere from what? 0, 10 volts. Okay. But it's not a power source. So to make the pot work, I've got to have a power source, right? So what I'll do is this is the way the circuit's been modified. So I'm going to come over here, and I'm going to come over here. I'm going to put a pot, wired as a pot. And then I'm going to come over here and put my variable power supply right here. Now, to decide what voltage I needed, I looked at the maximum current that would ever have to run through the 33K. What's the maximum current we have in the chart for IB? What's that? IB. What's the maximum voltage for IB? Base current. Somebody can tell me that? Base current across the top. What's the maximum current I need? 150 microamps. What voltage would I need across my 33K to get 150 microvolts? That's a crummy symbol for a pot, by the way. But I should have drawn the pot first. So what voltage do I need? Oh, about 6 volts. Okay. And once I got this set, so I'm going to set this to 6 volts. And in that way, I can adjust it where I need it at, right? Everybody understand? Have I lost anybody? So this is the circuit I have. So what we need to do right off the bat, right up above your base current, calculate so we're not going to measure current. We're going to measure the voltage drop across this resistor right here, and we're going to use that to calculate current. A lot of people think to measure current, you got to break the circuit and put an amp meter. But if you got a series resistor in a circuit, that's the way you would measure current. What do? You'd measure the voltage drops, and then you would just adjust it till you get those voltage drops. So what we need is and write this above the chart, we need VB, and we're going to call that VRB. So we're going to need VRB for, we're going to need VRB for 50 microamps. We're going to need VRB for what? 100 microamps. We're going to need VRB for 150 microamps. Huh? Yeah, the top one we already had was 1.65. Is that right? 1.65. For 100 microamps would be twice that. What's that going to be? Just multiply that times 2. What's that? Can't be 2.3. It's got to be 3 point something. Yeah. And let's don't round. 3.3. And then 150 would be 3 times that. 1.65 times 3. What's that? Okay, so now we know the voltages that we're shooting for to get these different base currents, right? Now what we're trying to do is we're trying to develop what we call a collector characteristic curve. And what's up this guy right here? This is IB, and what's on this right here is voltage collector to emitter. So what we're going to do is we're going to start off with no bait. We're going to start off with 0 volts here, and then we're going to start increasing, right? Y'all understand what I'm saying? And what eventually is going to happen is the transistor is going to start turning on, and then it's going to, I'm sorry, I got this wrong. This is IC. And then eventually what's going to happen is this is going to level out, and it's going to have a slight slope because of the internal resistance of the transistor. And then we're going to come over here and we're going to go through how many different currents? 3. And of course, what we do here is we put IB right here, and this should be, we should have something down here for 50 microamps. And then right up here, this should be for what? 100 microamps. And this IB should be for 150 microamps. So if beta says, so beta, or H sub FE, is IB times, I'm sorry, what's the formula for beta? What's our input on? What's our input? So beta is a gain. Anytime you calculate gain, gain is always calculated by output divided by input. Gain is always calculated that. So beta is gain. So what's our input? What current is our input? Huh? What's the input current to a transistor, to this transistor? IB, IC, or IE? I hope so. What's our output current? IC. So that's beta. That's the way we calculate beta. Everybody understand that? So how do we calculate gain? All you got to do is figure out where the output is and where the input is. We divide it. And that gives us the gain. And current gain base to collector, we call this beta. It's also called H sub FE, which stands for the forward transfer current ratio for a common emitter amplifier. And this is common emitter. This is pretty obvious because the emitters take directly to common, right? Are we okay? Are we ready to start? So how are we going to measure IC? Huh? So the way we're going to calculate RC, so we're going to have to calculate our IC. IC is going to be equal to VRC divided by 100 ohms, right? Y'all understand that? Huh? Why don't we use beta? We're going to calculate beta, but we're not going to use beta to calculate IB. Somebody tell me why. Well, why are we not going to use beta to calculate? Why do we stay away from beta as much as we possibly can? Well, no gains has units. I don't mean you stay away from it. Okay, so I'm going to go to Blackboard, and we're using a 3904. And I'm going to look up the beta for a 3904, and then you tell me why I don't use beta. So here's the, we'll go to data sheets. Go to 3904. By the way, in data sheets, they label it H of FE. You won't see beta. About the only time you see beta is in a book. I'm going to go out here and find H of FE. And there it is. Oh, my goodness. Okay, tell me which beta do you want to use? Do you want to use 40? Do you want to use 70? Do you want to use 100? Do you want to use 60? Do you want to do 30? Do you want to use 300? What do you want to use? All I know is beta is going to be somewhere in that range. So we'll calculate beta, but we won't use beta to calculate because we don't know what it'll be, right? It varies with base current. It varies with collector current. It varies. So beta varies all over the place. It varies with temperature. But we can calculate the beta of the circuit, but we're not going to use the beta of the circuit to calculate, right? Understand, Barry? Why? That would be like Legion Field. You going up to Legion Field, or you go up to Legion Field and you park your car, and then you go up there and you say, go by. You tell somebody to go find your car. You know, it's going to be really, really hard. Why? Because your car could be where? Anywhere, and that's the problem we have with beta. So beta could be anywhere between. All I know about beta is it's going to be somewhere between what? 30 and 300. So we're going to calculate the beta, but we're not going to use beta to calculate. Understand why? So y'all know why. So when we're doing transistor circuits, we stay away from beta as much as we possibly can. But we can set a circuit to give us a certain beta, right? You'll understand that. But we don't use beta to calculate the circuit. So all we know is that if I design a circuit around this transistor, we need to make sure that it's inside the beta that we end up with is inside that range, right? Does that make sense? Yes, we can.